For the Go problems in Unit 3, Lesson 3, I'm only going to go over 2 of them in the video. I think I'm only going to ask you to try 21 and 22. We are asked to find both the explicit and recursive equations for the functions represented in the tables. I'm going to zoom in on 21. All right, so first thing I'm going to consider is whether or not I have a pattern of like addition or multiplication here. So as n increases by 1 each time, thankfully n is increasing by 1. It's kind of hard when the n values jump around. I notice that my outputs, my y values, because remember this is like x and y, my outputs are doubling. So I've got to check a couple points. I might first be like, oh, we're adding 4. But 8 plus 4 is not 16. However, 8 times 2 is 16. 16 times 2 is 32. So that tells me that this function is exponential. And I'm actually going to start with the recursive rule because I think that might be easier. So if I'm looking at my recursive rule, if I want to get to some f of n, I'm going to take my previous term. So that's where my n value is 1 less. So for example, if n is 5, f of n minus 1 would be, well, f of 4, because 5 minus 1 is 4. So that's why we think of that as our previous term. And I'm going to multiply that by 2. So you could write it out there. I could have stuck the 2 out in front of that. Remember, my recursive rule is not finished until I've given a value in my table. Like an initial value, or it really could be any value, but maybe it should be our initial value. Okay, so that's a recursive equation for this. Now, for an explicit equation, the reason this is a little harder is that we don't have the y-intercept in our table. And we can find it, but we don't have to. I'm going to erase this over here. And I want to show you, it's similar to what we do with point slope form. We don't call it that because this is an exponential function. It's not linear. Maybe we could call it point growth factor form. That works for me. So here's how we could think about it. I could say, all right, when I think of, I know I'm multiplying by 2. That's my growth factor. So to get to the number 8, starting at the number 4, that's 4 times 2. To get to the number 16, that's 4 times 2, which was 8, times 2 again. And to get to my 32, that's 4 times 2 times 2, that gave me 16, times 2 one more time. So as I go to generalize these, I could think of this. I'm going to condense this into exponential form. This is 4 times 2 to the 3rd power. This is 4 times 2 squared. This is 4 times 2 to the 1st power. I'm starting to see a pattern with these exponents. So is it true that this is 4 times 2 to the 0 power? Yes, because 2 to the 0 power is 1 and 4 times 1 is 4. So look at the exponents and compare them to the n values. We should notice a pattern that whatever my exponent is, it's always 2 less than the n values. So I could really write this, and this is how we're going to get there. I could really think of this as 4 times 2 to the 5 minus 2 power, right? 5 minus 2 gives us 3. This is 4 times 2 to the 4 minus 2 power, since 4 times 2. And if you're like, wait, why am I writing it this way? I'm trying to incorporate these values in our exponent. So this is 4 times 2 to the 3 minus 2 power. And that means this is 4 times 2. Oops, nope, that's not how you write that. 4 times 2 to the 2 minus 2 power. So now I can see, oops, I don't know what's going on with my computer or my pen. I hope my video didn't just cut out. I've been having a few tech issues as I'm filming this. Okay, That's supposed to say 4 times 2 to the 2 minus 2 power, but it's not letting me write. I don't know what's happening. Sometimes OneNote gets angry with me. It could be OneNote. I'm not sure. Okay, well, I can't fix it. It's not letting me. Oh, well, let me write. Oh, sometimes it does this. I'm not going to quit. I'm just going to keep rolling with this. So look at this form. Look at where, now it's working. Look at where n is. So I could write this explicit equation as f of n equals 4 times 2 to the n minus 2 power. Now remember, we don't call this point slope form because it's not a linear equation, but it's the same idea. I started with an output of 4, and that's where my n value was 2, so that's why I have n minus 2 as my exponent. That's one way to write this equation. Now, some of you might have gone back and just found what would happen when n is 0. So if I try to do that, let's see if OneNote will stop being disagreeable. If I go backwards in my table, oh, it's being disagreeable. If I were to have an input of 1, that means my y value would have to be the number that when I multiply by 2, that gives me 4. So working backwards, I could think of I'm dividing by 2. So that would be a 2. And if I go back to where n is 0, 2 divided by 2 is 1. So if anyone wrote the equation f of n equals 1 times 2 to the n power, that works as well. Okay, that's number 21. 22, I think, is a little bit easier. The reason I think it's maybe easier is it's linear, and it's another good chance for us to look at point slope form. So the way I know it's linear, maybe I spoiled it, is that I'm seeing a pattern as n increases by 1. I'm seeing a constant rate of change here, a pattern of subtraction. So I'm subtracting by 4 as n increases by 1. So for my recursive, for some reason my brain wants to start there. You can do the explicit first. I'm going to find my desired term f of n, I'm going to take my previous term and subtract 4. And remember, I need to provide a starting point for my values. So that's a good recursive equation right there. For my explicit, again, I can use point slope form, but remember, if you're confused about it, I know we were assessed on point slope form in Unit 2, that last learning target 2C. I'm going to erase this so I can write something else here. We can come up with it organically in our table if we forget the form. So let's remember, I'm decreasing by 4, so I could think of 19 as 23 minus 4, wherever I started. I'm going to use this as my starting point. I could think of 15 as 23 minus 4 again, and I could think of 11 as 23, but I've now had to subtract 4 3 times. So if I condense that, if I condense my repeated subtraction, or let's think of this as repeated addition of -4, this is like 23 minus 4 one time. This is 23 minus 4 2 times. This is 23 minus 4 3 times, which must mean that this is 23 minus 4 0 times. Well, that makes sense. So again, I want to look at the only thing that's changing in this expression and think, how does that relate to n? And here's our hint. It has to do with the number 6. It has to do with the n value where we started. The expression in here is always my value of n minus 6. So 9 minus 6 gives me 3. 8 minus 6 gives me 2. 7 minus 6 gives me 1. 6 minus 6 gives me 0. So I could generalize this that for any n, I'm going to have 23 minus 4 times whatever n was, but less 6. So that is one way to get to my, that is maybe a more organic way to get to my explicit equation, 23 minus 4 times n minus 6. But again, I could think of this as point slope form because this is linear. So we sometimes say point slope form is like, x minus x sub 1 and then plus y1 here. If my ordered pair, x1 comma y1, if that ordered pair is 6 comma 23, well, if I plug in a 6 here and a 23 here, I have the same thing. I'm going to go back to f of n down here. You can use y. I don't really care that much for the explicit. It's hard to do that with the recursive. I could think of this as negative 4 times, if I'm using n, I should use n here, n minus 6, and then plus 23. These are the same thing. I just wrote the 23 out front in the orange one.